The data don't lie, people do.
Before I jump into this deep dive, I need to make some corrections from the last video. Every time I opened up my CSVs in Numbers on the Mac, it spell corrected everything, and I was so focused on getting the information out I didn't notice. So in this video, I turned all those features off in Mac Numbers so it doesn't keep doing that, along with multiple other annoying settings that it has. So hopefully what I'm showing on the screen this time is more accurate. The first thing I want to point out is that Jessica Hyde's demonstration, when she first put this table up to show us what she found where, actually gives us the complete URL, the entire string that was sent to the server and returned from the server. The same with this particular table here that we were looking at, showing us the page salts. So for those columns that Ian Whiffen had collapsed, I have added the rest of the string. So after house long to die in cold with the little pluses in between, the server responds with IE equals UTF-8 and OE equals UTF-8 and the English language US and the client is Safari. As I explained in the last video, that's proof that the server received the request and sent it back, i.e. the search request was completed. The reason we couldn't see that entire string on the screen when Ian Whiffen was showing it to us is because he collapsed that column, most likely to fit it on the screen so that we could all see the other columns. The other column that was collapsed, which I'm unable to rebuild because nobody gave us screenshots of that column not collapsed, is the UUID. But we do see enough of the UUID to tell when it's the same tab being referred to or when it's a different tab. This is depicted here in the first 8 characters in the browser state DB. The other thing I've done for this demonstration is I have taken multiple exhibits showing us snapshots from different parts of the databases and I've put them all back in as one table. So all of the snapshots of Knowledge C I concatenated into one table, all the snapshots of History DB I concatenated into another table, and all the snapshots of Browser State DB. These came from exhibits 614 right through to 626 from trial 1.0, and I also added anything extra that was different or that we didn't have previously from trial 2.0. What I can't tell you is whether records are missing or what order they should be in when it comes to Knowledge C DB. The best we can do is cross-reference with other databases. And it doesn't have a write-ahead log like the other databases do either. History DB, however, does give us a little bit of sequential ordering in the history visits column. So in the original screenshots from court, this column was called Source ID. I've since worked out that this is history visits. So we have the visit count, which unless you're an Apple developer, you can't actually be sure that it's counting unique visits or every visit. It would make life a whole lot easier for us if it was every visit because it doesn't increment every visit. So that doesn't really prove anything. But this last column, originally labelled Source ID, I have now relabeled it History Visits because you can see those are in sequential order. And my research indicates that this is actually the count of total visits. So that gives us a little bit better idea of sequential records versus dates because we're pretty sure they've been screwing with the dates. And then in Browser State DB, we have the row ID, which is sequentially ordered, and then the order index, which tells us which tab was on top of which. So a higher order index is a more recently viewed tab on top of everything else. Now, I have added a status column to the Browser State DB just for reference as to what Ian Whiffen testified that they mean. Some of them were recovered from the WAR file, so he did some data recovery apparently, and some of it existed in the original Browser State DB. So when you hear Ian Whiffen say there was no gaps in the row IDs, there actually were. He actually had to go and do some data recovery to find those gaps. So what I can tell you about putting all of those exhibits together into the browser state DB is that they are in sequential order. So we do have all the data for records between 4021 and 4039. There's a few missing before that, but they're not in the date range that we're looking at. So that's the overview of all of the concatenation of data that I put together for this demonstration. I want to start with Richard Green's discovery of the "How Long to Die in the Cold" search in the write-ahead log. It tells us in the source column that this snippet of information was found at location 0 times 298 AC1. We can convert that, it's called an offset, and we can convert that into decimal and then look for that decimal offset in Jessica Hyde's salt table. So in decimal, this is 2,722,497. Looking in Jessica Hyde's table, we see frame 660 has an offset of 2,722,247. The difference between Richard Green's offset and frame 660's offset is 250 bytes. So this is within the same frame, because they're typically 4096 bytes, as commit 54, the last commit. That's the final state before everything was deleted for the 2:27 AM search. Ian Whiffen's demonstration actually stops short of frame 660. I wonder why that is. But he does, however, tell us that row 4028 was still present after row 4029, 4030, 4026 and 4027 had all been deleted. And that tells us it was most likely still present at frame 660. The fact that Jessica Hyde showed us row 4028 still existed at frame 660 is all we needed. We can reconstruct the 2:27 AM session by correlating timestamps across all three databases. This is basically the same process described by Whiffen and Hyde in their testimonies. So let's start with browser state DB. It shows us that PayPal, row 4024, and Eastern Bank, row 4025, were visited at 2:27:31 and 2:27:33. Knowledge CDB confirms these same pages on screen at the same times. History DB shows the next actual navigation was Hockeymock standings at 2:27:42. This is listed as visit number 31458, which matches Knowledge C for the exact same time. This temporal correlation proves which events actually occurred versus which are fabricated. If we flip back to browser state DB, row 4026 claims the Hockeymock gallery page was visited at 2:27:35 on January 29th. We can verify this by cross-referencing with the other databases using that timestamp and URL. History DB shows us the same URL was visited on January 27th. This is marked as visit 31407, not January 29th. Knowledge CDB shows us this URL appeared on screen at 2:27:37 for only 1 second. Some might argue this is consistent with tab switching rather than actual navigation. And the final method that we would use is called presence versus absence analysis. And Ian Whiffen testified to this himself in both trials, only he came to a whole other conclusion as to what absence actually means. As we covered in the last video, browser state DB should show us the tab state changes, open, close, focus. History DB should show us the page navigation, any new URLs loaded, for example. And Knowledge CDB should show us what's visible on the screen, what was actually displayed. For example, browser state DB, row 4028, claims that the Google search, "How Long to Die in the Cold," was made at 2:27:40. HistoryDB has no entry, but let's assume some searches don't create history. Not finding an entry in HistoryDB would be to be expected. In KnowledgeCDB, we would expect to see the search URL visible on the screen at 227.40, but what we see at 227.40 in KnowledgeC is actually Ozone Basketball. This is a mismatch with browser state. Ozone Basketball could not be on the screen at the exact same moment, down to the second, as the incriminating Google search. This proves that the Ozone Basketball timestamp is faked. So essentially, we're just using the same methodology that Whiffen and Hyde both described, but we're coming up with different results because we're not looking for the same answer. We're not looking to prove that 2:27 AM didn't happen. We're just looking at what order did things happen in. Before I get into what order I think things did happen in, I just want to address what I found in my research about the suspended state tab timestamp, because I wouldn't be doing anybody any favours by avoiding it and not explaining why this is not that. There is in fact a legitimate ambiguity that the forensic community acknowledges, and it is generally described the same way that Whiffen and Hyde described it. The last viewed timestamp could mean option A, when the tab was first open, like the user opens a new tab, timestamp records that moment, tab content changes later, and the timestamp stays the same. Or option B, when the tab was last brought to the foreground, the user switches to an existing tab, timestamp updates to that moment, shows the last time the tab was focused. Or option C, when the content was last updated. So the tab is already open, new navigation or search happens, and the timestamp records when the content changed. This is a real ambiguity in mobile forensics. Surprise, surprise. But the meaning depends on the context. So Hyde's and Whiffen's arguments are plausible based on this known ambiguity. They said the 2:27.40 timestamp is when the tab was opened or focused. The actual search content, house long, was added at 6:24 AM. The timestamp doesn't update for content changes, so 2:27.40 equals tab focus time, not search time. And if this were the only evidence, they probably would win this argument. But that's not what I'm trying to show you. In the previous video I showed you that they weren't the same tab, and that Hyde's own salt table shows us that all of these things regarding the house-long search happened in one session. And then in this video, I want to show you the structural impossibilities. This has nothing to do with the timestamp. There's a structure problem, besides the fact that we can clearly see they're not the same tab UIDs. In Jessica Hyde's pizza restaurant analogy, she never once mentions that the waiter knows which table or which customer at which table ordered what food because of their table number. I hate to flog a dead horse, but let's listen to her testimony again about the restaurant analogy.
So there's two really key elements as to if that was user deleted. If the question is, did I come to opinion? Yes.
And can you explain how you came to an opinion that we'll ultimately share with the jury?
The first line in that exhibit, the ending of that, if you remember, it said browser state.db-wall. That's important, so we'll talk about that in a second. But the first thing I want to bring up is kind of how the database works, because I didn't just look at the tool result. I extracted that database and I did a deeper analysis on it using Sanderson's tool, because that information was in that dash wall file. So when a SQLite database, which is a specific way of storing, very, very common on mobile phones, actually one of the most common.
Let me also add here that SQLite, or she's calling it SQLite, which is, I guess, another name for it, is not Apple proprietary software. It's actually open source public domain software originally created by Dr. Richard Hipp. Anyone can download the source code from sqlite.org, anyone can read the documentation, anyone can test it themselves, and anyone can become an expert. Yes, Apple uses SQLite in iOS, but they didn't create it. They don't own it.
When that database stores data, it has two versions. The most recent version and the version in use here uses what's called a write-ahead log. So before data is committed, it is written to a write-ahead log.
Yet her own table that she shows you, that she found with the SANS tool, has recorded 29 commits over 16 records.
I'll kind of explain it. So let's say we're in a restaurant and we're sitting at a table and we're ordering food. Our table is the table. Data is going to come to the table, and that's going to be our food. So when we order food, let's say we've got a chicken sandwich, a burger, and a pizza coming to the table. The chicken sandwich, the burger, and the pizza, the kitchen puts it in the warming area. It's the write-ahead log. The server grabs it from there. It's where data sits before it goes to the table, just like your food goes to that serving station before your server brings it to your table.
Which table? Just like Whiffen, she talks about the specific tab, this table, and she never says which table. You don't need to be a qualified restaurateur to know that when you take an order, you have to write down the table number so you know who you're delivering the food to, and so that you know you're paying the right account when the customer comes to pay for it.
Table server brings it to the table. That table's got its burger, its chicken, and its pizza. Another table
means another table number, right? Not the same table, a different table.
orders waffles and pancakes. They think it's breakfast. The waffles and pancakes are made by the kitchen. They're put on the serving area. The waitress comes over. This pizza has pepperoni. I don't eat pepperoni. Can you send it back? Waitress picks up that pepperoni and sends it back. That's a deletion. Pepperoni pizza was just removed from the table, right? We're deleting it. We said it's not what we wanted. The waitress is removing it. She brings it back to that serving area. At that moment, that serving area has the deleted pizza, but also the waffles and pancakes that are waiting to go out to the table. That's how a write-ahead log works. Any changes that are happening sit in the write-ahead log until the database is closed, and then when it's reopened, all those changes are made, both additions and deletions.
So let's have another look at her salt table. She said that data waits in a warming station before being delivered, and for uncommitted data that's true. But these 16 wall frames show commit numbers 25 all the way up to 54. That's 29 commits. In database terms, commit means save this, make it permanent, it's done. Committed data isn't waiting, it's been served. So why is it in the wall file 16 times with 29 different commit numbers? Because someone kept modifying it and hitting save 29 times. So it's not food waiting to be delivered. This is someone editing an order that was already delivered. 29 attempts to change history, and SQLite recorded every single attempt. Now, looking at the salt column, think of this like a session ID. If you close the database and reopen it, you'll get a new salt number. These 16 wall frames have the same salt, 4044. That means one database session, it was never properly closed, all modifications in one sitting. It can only mean one person, one computer, one tampering session. If this was normal Safari use from 2:27 a.m. to 6:24 a.m., Safari would have opened and closed the database multiple times, so we would have seen different salt values across those hours. And look, I want to be fair to Ms. Hyde. Explaining SQLite to a jury who's never heard of a write-ahead log isn't easy. A restaurant analogy isn't the worst idea, and she's right. The SQLite writes to the write-ahead log first, then checkpoints to the main database later. A checkpoint is the opening and closing of the database. It's different to the commits. So, the write-ahead log is a staging area concept. Pizzas ordered, warming station, delivered to the table, data written, wall checkpointed to the main DB. That part's not terrible. But here's where the analogy breaks down. She said the data is waiting when it's actually committed 29 times. Then she said deletions go back to the warming station, not how the write-ahead log works. But there's also some other flaws in her analogy. For example, let's say one table said, I'll have a pizza with anchovies, and then the next table said, I'll have a pizza but hold the anchovies. The differences are subtle, but they're different nonetheless. Let me explain. Her write-ahead log data shows us that all 16 orders were for the same pizza. The same pizza for the same table for the same eating session, if you like. But KnowledgeDB tells us that they were different orders. 62356 was a hold the anchovies order. Spelled how long TI die in CIKD. This is a distinctly different order to how long to die in cold. But also note the duration. The 62356 one only lasted for 1 second. The 62357 through to 62424 lasts 27 seconds. The time, together with the return value from the server, i.e. equals UTF-8, etc., tells us the search was completed. The subsequent pizza order, which is spelled differently, was ordered at 10:33 a.m. We can also see by the Z object ID that these are 3 different database records, or 3 different pizza orders if you prefer. That's problem number 1. Problem number 2 has to do with SQL's automatic sequence numbers. Remember in the last video I told you can't mess with the row ID because it's automatically assigned by the SQL database. The only way you could mess with it is leaving the row number there and copying and pasting the timestamp and the URL into that row. So when we look at row 4025 right through to 4031, they appear to be in the right sequence. In normal operation, next row ID would be 4032 and then 4033, for example. So the row IDs look right. What doesn't look right is the dates. So let's revert back to the restaurant example. Table numbers are sequential. Table 15 gets seated before table 16. But in this database, table 4028 ordered on January the 29th, but tables 4029, 4030 and 4031 ordered on January the 26th. So either we have a case of time travel or we have database tampering. This order is impossible because SQLite assigns row IDs sequentially or auto increment. Each new record gets the next available number. Row 4029 created after row 4025 because it's a higher number, but it has a timestamp from before row 4025, which is an earlier date. You can't create row 4029 on January the 26th when row 4025 already existed at a later date. This is mathematically impossible. It's not even an interpretation. It's mathematically incorrect. Problem number 3. We've already touched on this record a little earlier. This is row 4026. In the browser state DB, we see it was recovered from the write-ahead log. It claims Hockomock Sports Gallery was visited 22735. We already established that there was no history DB entry for January the 29th for that record. There is, however, 2 visits to that address, numbered 31407 and 31408. Last visited January 27th, 2 days before the claimed 227 visit. And then Knowledge CDB shows the gallery page on the screen very briefly, but this is 2 seconds after browser state timestamp. This tells us that that page was not navigated at 227.35. Row 4027, the YouTube Weather Girls video. This timestamp tells us 227.38. It also tells us it's been recovered from the write-ahead log, but HistoryDB tells us there were multiple visits on the 27th, visit number 31398 and 31402 at 4:58 p.m. There is no entry for January 29 in the HistoryDB. Knowledge CDB indicates that URL for the Weather Girls was only on the screen for 1 second, certainly not long enough to listen to the Weather Girls singing. This Knowledge C activity could be tab switching, but one thing is for certain, the page was not actually visited on January 29th at 2:27:38. Row 4030 for Ozone Basketball. Browser State DB shows us the timestamp of 10:33:35, recovered from the write-ahead log. HistoryDB shows us 2 visits to that address, 31128 and 31129. It says January 25th was the last visit. There's no visit on January the 26th. So the last visit day of January 25th is a day before row 4030 claims in Browser State DB. Knowledge C shows us multiple entries around 2:27:40 and 10:33:40 showing Ozone Basketball /league, which is a different URL than row 4030 claims. Knowledge C would appear to show legitimate ozone activity, but not at times and URLs that Browser State claims. So this record is obviously fabricated with timestamp from HistoryDB. Problem number 4 involves a broken visit ID chain during the 2:27 a.m. session. HistoryDB tells us that history visits 31457 through to 31462 were visits to Friday schedule and scoreboard, hockey mock standings, hockey mock schedules, girls hockey schedules, 2021 to 2022 Franklin girls hockey schedule, and hockey mock standings. However, Browser State DB tells us that visit 31458 is supposed to be hockey mock gallery and 31459 is supposed to be YouTube. If they were visited, they would be in those visit ID positions, but the actual 31458 visit is a different page at a later time. It proves those navigations didn't happen. Problem number 5. Row 4031 has a timestamp discrepancy. In Browser State DB, it shows 2 different timestamps for the same UUID. Already existing in the database was UUID BE9E 8EAF, etc., with a timestamp of 6:29:55 on the 31st, and an order index of 13. Recovered from the write-ahead log is the same UUID at timestamp 9:50 on the 25th, 6 days earlier, with an order index of 9. So we have the same row ID, the same tab ID, but different timestamps and different order index. This suggests the record was modified. And finally, problem number 6. In Trial 1 testimony, Ian Whiffen claimed that the user must have closed Safari at 6:24 a.m. while the search was loading. He said he couldn't reconstruct session history for row 4028 because the data spanned several pages and the pointers didn't make sense. We already debunked the data spanned several pages in the last video. We know it was all one page, thanks to Jessica Hyde's salt table. His reference to pointers, though, flew right over my head until Alexis K raised it. So what pointers was he referring to? The only thing we can deduce is he was referring to pointers in the SHM, or the shared memory. And he didn't mention those pointers in Trial 2 testimony because he completely switched his story that the user had to have completed the 6:24 a.m. search because of the little pluses and the IE equals UTF-8 string. In Trial 2 testimony, he testified that she'd merely backgrounded Safari, she didn't close it. And so the contradiction between the two testimonies means that if Safari backgrounded, which he said in trial 2, then the session continues and the pointers would be valid, so he should be able to reconstruct it. If Safari closed while loading, which is what he said in trial 1, then the pointers would be corrupted and they can't be reconstructed. These two suggestions are mutually exclusive. You can't have it both ways, Mr. Whiffen. What shared memory corruption actually indicates is that shared memory contains pointers to the wall frames. Valid pointers means you can reconstruct the session. Invalid pointers means that you can't. Corruption indicates improper database shutdown. Or the database wasn't edited on the device, it was edited on a computer, and so the SHM wasn't saved back to the device. In my humble opinion, I think the SHM corruption proves external tool usage. In any case, Ian Whiffen can't explain it away with she backgrounded Safari, because if Safari backgrounded properly, then the shared memory would be valid. If this were just one red flag all by itself that could indicate external tool usage, then maybe a forensic examiner would ignore it. But now we've identified dozens of red flags between this video and the last video. So just to wrap up, here's the undeniable facts. 2 searches with different typos, house long and how long TI. Clearly it's 2 different orders. One's pizza with the anchovy and the other one's pizza without the anchovy. Backwards row IDs. For example, 4029 on January 26th comes after row 4025 on January 29th. Mathematically impossible. Fabricated records proven. Row 4026, 4027, 4029 and 4030 all have discrepancies between the different databases. Sequential visit IDs prove no navigation happened between certain events claimed in browser state DB. SALT 4004 proves that this was a single session across all frames, and it contradicts a 16-hour deletion timeline by the system. And finally, the shared memory corruption. You can't have it both ways, Mr. Whiffen. Either the pointers don't make sense and you can't reconstruct it because it was improperly closed, or the pointers do make sense and you chose not to reconstruct it. This analysis is not interpretation of a specific timestamp. There is no ambiguity here. This is mathematical proof. And, well, you know what I always say.
The data don't lie, people do.